Well, good morning. Well, this is our current topic, capacitors, and yesterday we have learned how to calculate the equivalent capacitance for different situations. And of course, first step is to draw a circuit. Also could call it a diagram, which represents this situation. And of course, you also can quickly eliminate answers which don't make any sense, so to concentrate on the answers which may make sense. For example, the capacitor, single capacitor, has capacitance of C farads, and if we are adding more capacitors to it in series, for example, capacitance has to change, so it just can't be same anymore. Plus, we cannot add or subtract physical quantities if they have different units, and numbers in capacitance cannot be added or subtracted together. Plus, the final answer should have the same unit farads, not 1 over farads. And definitely we have never had an equation when we have to raise to a power. And definitely that cannot be all of the above because they contradict each other. So theoretically it could have been none of the above, but in order to choose that answer, you actually have to solve this problem, look at your answer, and see if your answer is either one of those left or something different, right? So, picture. So I don't know how many n now we have two equations. To choose from. Come on. And, well, please tell me, raise your hand if you choose equation number 1 to solve this problem. If you choose equation number 2, well, sometimes it is helpful to remember that when capacitors are connected in parallel, the equivalent capacitors goes up relative to individual capacitance because we are just adding more area. But if we look at capacitors connected in series, basically that means we're moving away from each other the plates of the capacitor. What's inside doesn't really matter for this, reasoning. And if we move away the plates, the capacitance decreases. So it cannot be equation number 2, you're right. Also wrong for this situation. And all we have to do now is just finish calculation. 1 over equivalent capacitance will be equal to 1 over C n times, because they are identical. Hence, now we flip it over. And this is a handy fact which we always can use when identical capacitors are used. So for the connection in parallel, since we're adding n identical numbers, the result is just individual capacitance times the number of capacitors. Question. This is a new problem. Hasn't been solved yet. Capacitors are the same. 1 microfarad, 2, 3, but they wired up differently. The circuit is different. And again, if we look at capacitors 1 and 2, they are connected in series, nothing in between. Opposite plates are connected. But the question is about capacitors 1 and 3. So if it looks like this, answer is in series. If it looks like this, the answer is in parallel. If it doesn't look neither, the answer is neither. What's next? Yeah. And what is wrong with saying that these two capacitors are in parallel? This is how in parallel connection looks like. But what we do, we physically break it right here, and we are inserting an extra element, the capacitor number 2. And that's it. This is not same as this. You can see. So this would have been parallel. This is not. And of course, it's not in series. So the answer is, again, neither. But again, we can calculate the equivalent capacitance for this circuit and more charges, energies, if we want to, by folding it step by step. So every time when we have a complicated circuit, first we are looking for a part of its circuit which is definitely in series or in parallel. And this is the part which tells us these two capacitors, C1 and C2, are connected in series. So we can replace them with one capacitance. And to do that, we have to apply again the rule, and 3 over 2, so C2 over 3 microfarads. Now we have to redraw the circuit. The new circuit now has to show only 2 capacitors and the battery. We didn't touch the battery, so it remains 6 volts here. We didn't touch the capacitor number 3, it remained the same. But now we have replaced two capacitors, 1 and 2, with one capacitor, 1, 2. And now these two capacitors are in parallel. Now we can see it. So now these two can be replaced with one. And the capacitance of that equivalent capacitor will be equal to the sum 2/3 plus 3. 3 times 3, 9, 11 thirds microfarad. Okay. And this will be our equivalent circuit now. The battery and the capacitor. Finally, when we have only one capacitor left connected to a battery, we can start calculating other things. What other things? What can we calculate? Charge. As long as for the same capacitor, we know 2 out of 3 variables. We can calculate the third one, which 2 doesn't matter. So the equation tells us that for any single capacitor, these variables are related by a definition of capacitance. Again, technically, it's the voltage. So if we apply this equation to the last remaining equivalent capacitor, it gives us 11/3 times 6, 22 microcoulombs. Now we can go back to the previous situation, the previous schematic. Now, this charge split, and actually we could have calculated the charges by applying this equation twice, because when capacitors are connected in parallel, they share voltage. Yes? Cannot hear you.
When you did the 11/3 times 6, you don't have to make the volts into
What do you mean? I just used 6 volts and microfarads. No, I actually kept 6 volts, but 11 micro means 11 times 10 to the negative 6, so it automatically gives micro for coulombs. The same power, you know, I transfer it. So now we can calculate these charges, but if we go back from this situation to this situation, so the charge number 3 will be given by this expression, and actually we could have found it at the very first step, because the capacitor number 3 is directly connected to the battery. But the charge Q2 and Q1, they should be just equal to Q12. And if we know all the charges, all the capacitance, voltage, that's what we may need to calculate. Let's say we need to calculate this voltage, delta V1. Well, if we know charge and capacitance, we can apply the same equation, but just for the voltage, delta V1 will be equal to Q1 over C1. We can apply the same equation to calculate voltage 2, but also voltage number 2 will be equal to 6 minus the voltage number 1, because together they have to be equal to, together means if we add them up, they have to be equal to the voltage of the battery 6. So these are all the connections, nothing new. All right, I only needed one slide. So please tell me what you think about this question. We saw the demonstration. We saw there is a difference between a case when the capacitor remains connected to a battery and when the capacitor is disconnected from the battery, and then we make some changes. In this situation, the capacitor is still connected to the power supply, remains connected. This word remains connected tells us what will not change. Every time we have to search first for what will definitely not change, will be the same. For this situation, out of 3 variables, well, technically 5 actually, what set of variables do we have associated to any capacitor? Capacitance, charge, voltage, but also energy, and well, there's electric field inside. So in general, we have 5 different variables to think about. But every time, there's at least one which definitely stays the same, remains constant. So in this situation, what do you think remains the same, no matter what we do? What do you think? Delta V, because when a capacitor or anything else, yeah, we're going to talk about resistors today, I hope. When something is connected to the battery is the source of that voltage, delta V. So, but if V remains constant, automatically means that Q changes. How? Well, for that, we just have to analyze the equation. So the capacitance is proportional to area, inversely proportional to distance between the plates. The exact equation, K, epsilon naught, doesn't matter. So if the distance between the plates increases, that makes capacitance lower, decreases. That's what we know. On the other hand, charge, capacitance, and voltage related by this equation, a definition of capacitance. And if the voltage remains constant, that automatically means what happens to capacitance, that same thing happens to the charge. If capacitance decreases, the charge decreases. That's it. So the answer is Q decreases. The answer is 1. So this slide tells exactly what I said. And it's not a question, but let's say we want to go further. Energy. For the energy, we have 3 possible equations. Yeah, 1/2 Q times delta V, 1/2 C times Q squared, 1/2 oh no. Q equals C times delta V 1/2 C times delta V squared. And technically, I should use absolute value and 1/2 Q squared over delta V equals Q over C over C. Now, what changes? C and Q, which means the last equation is the least convenient when an equation has two variables which both change. We cannot really predict the effect on the combination. So we should choose the one which has one constant and one changing. For example, this or this doesn't really matter. We know both. So if the voltage remains constant, but the charge decreases, the energy decreases. So we always need to search for the easiest approach, and the easiest means at least one variable in the equation must be constant during the process. So we just look at another variable, and that's it. Electric field. Well, that's what is happening. And nothing is happening in between. So, and the voltage remains constant, which is very important. So we should search for the equation which relates that voltage, electric field, because that's what we're looking for. And what else? Well, distance. If the voltage remains constant, but distance what decreases? No, what increases? Distance increases. Electric field decreases. It's inversely proportional. We increase the distance, electric field goes down. Electric field might be affected also by a dielectric. If we insert a dielectric, remember, in that case, electric field decreases. Well, again, these are very common situations. Let's talk about one more. You have a capacitor which was initially connected, charged to a certain charge, and then the battery is disconnected from capacitor, and only after that we start moving plates away from each other. So, well, in this situation the question is just about delta V, but of course the search, the first search is for a variable which doesn't change for sure, which should remain the same, constant. And in this situation, when the capacitor is not connected to battery, basically to anything else, what should remain constant? Charge, exactly. So that's the first thing we have to say. What will not change? All right, the rest is easy. Do we have a slide? So, Q remains constant. So, when we increase the distance, we know we decrease the capacitance. This is just a feature of the capacitance of a parallel plate capacitor. So, when we increase the distance, we decrease the capacitance. This is not new, this is the same as before. What is different? Now we have to solve it for the voltage the charge remains constant, but the capacitance decreases, so the voltage increases because it's opposite to that. And this is what actually we observed. This was the demonstration we did yesterday. Distance goes up and voltage goes up, distance goes down and voltage goes down. I was moving plates away and the meter was indicating the change. Any questions? All right, so that's the answer. And now, remember the difference between a conductor and dielectric. In a dielectric, we have to apply a very, very strong electric field to make a few electrons move. That actually breaks a dielectric. In a conductor, even a very weak electric field makes electron move easily. So what's going to happen if we take a conductor and place in an electric field? That's on the next slide. And I'm going back. So when we take a conductor and place in an electric field, electrons start moving, but they cannot move forever. Eventually, they should lose the energy and they should stop. It means eventually the equilibrium should be reached. And the equilibrium should be reached in this situation. That means that here, outside of the capacitors, electrons also cannot move. So the question was, let's say we have two capacitors connected in series. We know that the same number of electrons which is leaving this plate should come to that plate. That's the law of conservation of charge. But why would this charge be having the same magnitude as the charge on the opposite plate? And now we know there should be no electric field here, because if the electric field there not be equal to 0, electrons still would have been moving. And how can it happen? Well, this is a simple model, of course, but in order to not having electric field outside of the plates, the charges on the plates must have the same magnitude. If that is not the case, if one plate has a larger charge, that means electric field outside is not 0 yet, and electrons keep moving. So this kind of neat reasoning which tells us why, when capacitors connected in series, the charge on each capacitor should have the same magnitude. And now, an additional consequence of all this equilibrium thing is that inside a conductor, electric field also has to be equal to 0, because if it's not 0, electrons keep moving. And well, if it is 0, that means electric potential is constant, which means if we have a bulk conductor, if we have a large bulk conductor, it's not just surface equals equipotential line. It's not just the surface has the same potential. No. Inside of this conductor also will be constant potential, the same. So we don't have to charge it. We can, where is it? Here. We can just, my favorite bet. We can just bring a charged object close to it. We don't see anything here because we cannot see electrons, but they really move away. And the same is happening here. this is the equilibrium, the new equilibrium. We know now more electrons should be below than above, but I don't touch it, so it still remains neutral. But inside this aluminum everywhere, aluminum piece everywhere, there will be no electric field, and electric potential everywhere will be the same. But what about this? Can we get inside that? Well, not inside that, but inside this. So, let's see. I put it in a cage. Effects. Well, technically the cage has to be closed, but even now there is no, well, no, there is some effect. Slight, strong, not so strong. Now I close it. Work, strong. That's air. See, it's moving. It's not my bat, just air. But I have a better experiment, hopefully. I don't know. I have no idea what it is. Again, technically, it should be closed, but even not completely closed cage already prevented electric field to get to the radio. Well, this is the antenna, so as long as I start closing the antenna, that's it. Electric field cannot get into. And clearly, it's not related to sound. Yeah. We can speak through. So that's it, I just killed it. Well, not her, just electromagnetic waves. So this is what we call shielding. Inside a closed conductive surface, electric field cannot penetrate. It's zero. And how do we use it? Well, there are different ways to use it. For example, if you are inside a car, you're safe, because even if lightning hits the car, you are in a closed conductive surface. So electric charge just drains down. The car might be damaged, but not you. And now, the last demonstration related to capacitors. We can charge a capacitor plus to plus, minus to minus. So all we need is a capacitor and a source of the voltage. Actually, I should have checked it before. No, I don't know. We'll see. So I'm charging it. If a capacitor has a relatively large capacitance, it takes time to completely charge it. And okay, let's see. Now I want to discharge it. Just, yep. It, you know, when I shorten it, all the charge which I stored in the capacitor immediately ran out, and that made a little spark. Now what I have here, a bigger capacitor. This one has capacitance of 6,000 microfarad. And I used just 9 volts to charge that capacitor. This one, heavy duty, is connected to a high voltage power supply. How high? If you look at the scale at the meter, you can see how slowly it's charging. It takes time. Eventually it goes up to 5, 5.5, 6,000 volts. Well, it's not moving. You can hear the sound. It doesn't like it. Now it's charged. And if a person touches it, that person will be killed. I don't want to be killed. But what's the difference between a small spark and a big spark? You have no headphones. What do? Exactly. Actually, there's usually some residue. Okay. Phew. Now, the number of joules stored in this capacitor was very small. The calculation is right here. 60, 70 joules, something like that. It's actually not a very large number. 70 joules, right? So if you calculate potential energy, MGH, 1 kilogram times 10 gives you 10 joules plus times, let's say, 7 meters. So it's a potential energy of just 1 kilogram above the ground, 7 meters above the ground. If you release it, you don't see much dent on the ground. But if we would touch it, that wouldn't be good for us. Why? Well, the reason is that what affects us humans is not energy, it's how fast it's being released, which is a power actually, energy per second. So that's what we use when we need to revive somebody. Not as high as this one. But when a charge is leaving a capacitor, those electrons, they start traveling very quickly through the flesh. And if they travel too fast, they might damage that tissue. That's why it's kind of dangerous. 120 volts is not, very dangerous. I've been shocked many times, still survived. But something like that would have been dangerous. And when we have many, many electrons traveling in the same direction, we call it a flow, yeah? But not fluid flow. It's a charge flow or current. So this is just one of many demonstrations. One, we have to start study electric current. And to study electric current, we have to study properties of electrons traveling in the same direction. And we have to introduce many, many new physical quantities and then new laws which relate those quantities. So this is our immediate goal. And again, I start from a question, which someone asked me a day or two before. If you place a charge in electric field and let it go, how will it move? Well, if we place an electron in the electric field generated by two plates, like these, and you let it go from rest, how would it move? Up or down, left or right? And this question is basically a review question. How do we answer this question? We have to draw a picture which should demonstrate, which should show first electric field, then the force acting on a charge, and then we will see how it's going to move. So how should I draw electric field? Up, down, left, right? Why? From high to low, exactly. From high to low, that's electric field. Okay. How should I draw force? The relationship which connects it, force, charge, and field is given by this equation, which is a definition of electric field strength, but now we use it backwards. If we know the direction of a field and we know the charge, what kind of a charge is that? Negative. So the direction of a force should be what? Say it. Opposite to the field, and opposite to the right means to the left. And if we let it go from rest, it should start accelerating in the direction of the force. That's it. So now, if we have many, many electrons which can easily move, if we apply a potential difference, that potential difference might generate electric field, which exerts a force and make all electrons travel in the same direction. Of course, in reality, they all travel in all possible directions. That's a thermal motion. But also they drift together, like molecules in water when a pump make water travel through pipes. So drift velocity actually is very, very slow, about 1 millimeter per second. But they all start travel practically at the same time. If you have a very, very long wire and connect it to a power supply, all electrons in that wire start moving simultaneously. Slowly, but at the same time. And that's what we call electric current. And the magnitude of electric current, I, is defined as amount of charge traveling per second. That's a definition. A charge which travels over a long period of time divided by that time, charge per second. And the same equation tells us the unit, a coulomb per second, but that unit also has a name, an amp or ampere. Now, physically, electrons will travel in the direction of a force making them move. However, from historical reasons, because people at the time, when they studied this phenomenon, electric current, they didn't know anything about electrons yet. They didn't know electrons existed. So they thought that it could have been something like fluid traveling through wires, through conductors. So they defined direction of electric current opposite to the actual motion of electrons. And now we stick with that. Basically, a direction of electric current is defined in the direction of electric field, not electric force acting on electrons. That's it. From high potential to low potential. Sometimes it might be confusing, but it's just the way it is. If you can figure out the velocity of an electron, and the question is, what is the direction of electric current? Your answer should be opposite to actual velocity of actual electron. But again, it's easier just to remember from high potential to low potential in the direction of electric field. Now, from practical reasons, it is easier to imagine that we have fictional means not existing, positive particles inside a conductor. We can always ask, how would that imaginary particle move? And that would be the direction of electric current. So, positive electrons, yeah, or positrons. Now, we can solve many, many simple problems. For example, electric current, which is I, is equal to 0.17. That's not a Greek mu, that's regular lowercase m, so it means micro. And this means amperes. How much charge, that's Q, travels in 1 hour, that's time. However, the only tricky part is we cannot use hours or minutes, because according to a definition of a unit of amp, it has to be a coulomb over a second. So first we just have to convert time into seconds. And now Q will be equal to current times time, 0.17 times 10 to the negative 3 times 3600. That will be the charge. Point 6. Oh, 0.612 coulombs. That charge has been moved through the wire due to actual electrons traveling. So, how many electrons did travel? We know how to calculate. It has to be equal to charge divided by the elementary charge. 0.612 over 1.6 times 10 to the negative 12 divided by, oh, why 12? I don't know why. (1.6 times 10 to the negative 19th, right? What is the elementary charge equal to? Since I have no office hours on Tuesdays, my brain doesn't work on Tuesdays. 19? Well, that's exactly what I said. Lucky guess. So 0.612 divided by 1.6 negative 19th, 3.825. This is how many electrons travel in 1 hour through every cross-section of that wire. Okay, that's the answer. We have found number of electrons. Now, if we have a charge placed in electric field and nothing else would be acting on it, because of the force, it would be accelerating. F equals ma. And acceleration means it would have been traveling faster and faster and faster and faster forever. That's not happening. Why? Well, because every wire also has other parts. Nucleus is much heavier than an electron, so every electron collides with a heavy nucleus and get bounced back. Then electric field picks it up again starts speeding it up, but then it collides again, bounces back. So that's why the drift velocity actually is very slow. because electrons travel on average as a combination of back and forth, back and forth, back and forth, back and forth, back and forth. So this phenomenon has a name, resistivity. And of course, that property, resistivity, depends on the property of the material. There's big atoms, there's small atoms. The big atoms, more often collision happens, so slows it down. Also, it depends on temperature, because when we increase temperature, atoms start wiggling more vigorously, so they present more resistivity to the electron flow. Well, we don't need to know all the details, but on average, the force provided by electric field is being canceled by the force due to collision with atoms. And that's why eventually, if we set those forces together, we can make a conclusion that electric current, which is the representation of the average flow, not instantaneous. Yeah. The electric current is proportional to applied voltage. No voltage, no electric field, no electric current. Electrons just chaotically move in all directions. We apply voltage, it creates electric field creates force, electrons start speeding up, colliding with atoms, bounce back. Stronger voltage, stronger field, so they speeding up faster. That leads to more electrons traveling per second. And this law was derived experimentally by physicist Ohm, so we call it Ohm's law. This is the relationship between the electric current generated by applied voltage, and this coefficient has a name, resistance. And it depends on internal properties of a wire. It depends on how long the wire is, how wide, what is the material. There is an expression which relates the resistance of a wire with its length, cross-sectional area, and that property which basically a resistance of a 1 cubic meter of that matter. If we have 1 cubic meter of copper and measure the resistance, 1 and 1, that will be this coefficient which has a name, resistivity. How would we measure the resistance? Well, actually, it is much easier now than hundreds of years ago. First of all, we have devices which measure resistance. Secondly, we have devices which measure electric current and voltage. So if we measure electric current and voltage directly, then we can just divide voltage over current, gives resistance. Well, we're going to do some calculations like that. So this is a picture you should remember. This is what we call a passive element. Could have been a bulb, could have been a heat plate, could have been a projector, could have been anything which has a resistance. An electric current through that passive element always travels from a higher potential toward the lower potential. And the voltage, electric current, and resistance are related by the Ohm's law. That's it. And if we know how to relate these variables for a single passive element, we will know very soon how to relate those variables for a combination of those elements. All right. I'm not going to do this. I'm going to do this. Calculate potential difference between the ends of a wire. Okay. The long wire, maybe not the long, we actually don't really care. This picture represents an actual wire. For us, it is just a source of resistance. And there are two different symbols people use to demonstrate the presence of resistance. Something like this, a little box, or something like this. And we write a letter R, R. Well, of course, that's a specific type of a passive element, a bulb, a light bulb. Okay. Now, I don't know, I usually use a little box or rectangle like this. What we know is there has to be some voltage applied to it, and that's what we are looking for. The resistance is equal to 10. I forgot to mention the unit of resistance is ohms, and well, it's basically a volt over amp, but there are two different symbols to represent the unit of resistance. A Greek letter, capital omega, or people just write OHM. Don't write OMG. So, what else do we know? We know a charge, Q, which travels through this element per 1 minute. That's it. Now we know what we have to do. We just have to convert time into seconds. 1 minute is equal to 60 seconds. Electric current will be equal to charge over time. However, well, 6 amps. If we know electric current and if we know the resistance, we can just calculate the voltage, which is literally potential difference. Here, on one end of this element, there is a potential. Here, there is also a potential. When we have two different potentials, we have to use some labels, indicators, well, 1 and 2. And what does it mean? It means one is 60 volts higher than another one. Which is which? Well, we have to choose the direction of electric current because we are not told. We can choose it to the right. Let's say electric current travels to the right. That tells us immediately that the potential number 1 should be higher than potential number 2. Higher, what does it mean mathematically? Well, we can say V2 should be equal to V1 minus 60. Or we can say V1 should be equal to V2 plus 60 volts. We don't know the exact potential. We only know the difference here. Another situation. All right, so this is not about the Ohm's law per se. It's about two batteries. You see, two 1.5 volt batteries. What's the matter with it? Well, when we have two elements, we can connect them differently. So we have a bulb, we have a battery number 1, and the symbol for the battery is this. And the long line represents the positive electrode, short line represents the negative electrode. And then we have another battery. And, well, I can connect it like this. Or I can connect those batteries the other way. So here, in this situation, both batteries connected using the same electrode, negative to negative, could have been positive to positive. Yeah. Here, it's negative to positive. But only one connection would work. Which one? What do you think? The connection number 1 or the connection number 2? is used to? Well, first of all, a battery is like a pump. So in connection number 1, those batteries try to pump in opposite direction. We can draw electric field. Electric field goes from plus to minus. So inside this battery, electric field points to the right, but inside this battery, electric field points to the left. So they cancel each other. Nothing will happen. And, well, where is it? Here. Now it's a time to start doing something with the battery and the bulb. So how do we actually make a circuit? We have to use wires and we have to connect them. Yeah? So for example, this battery provides voltage of 6 volts. If I connect it to the bulb is on. Okay? So I cannot connect the wire to the insulation. It's not going to work. Yeah, we have to connect it to conductive parts. 1, 2. Now, I've got a second battery. And so middle to middle. That's what I want to do. Middle to middle. So now this wire should go to the free electrode on a second battery. Oh, okay. And what's happening now? Nothing. Because middle to middle means plus to plus, and that's not going to work. Okay, easy fix. We have to connect positive to negative. And you actually see it is brighter now. Why? Well, one battery gives 6 volts, 2 batteries now. 6 and 6 gives 12 volts. And of course, 12 volts means more power here. And we will calculate the power later. But we can see it is brighter. Dimmer, brighter. And what should we calculate now? Calculate resistance. Well, that's easy. Resistance equals voltage over current. Since we know the current and we know that the voltage will be combined from 2 batteries, that's a simple calculation. Any questions? Question to you. What's going to happen if we have 2 bulbs connected together in series? This, of course, is 2 batteries connected in series. No doubt. And a battery also has a different name, an active element. A passive element of a circuit, an active element of the circuit. Every circuit should have at least one active element and at least one passive element. That's it. And then we can make combinations of those. All we need is money to buy more bulbs and batteries. So what we have here is 2 passive elements, 2, we can say, resistors, 2 bulbs connected in series. Of course, they also should be connected to a source. We can imagine, or we can actually connect it to a source. There is electric current, we know it. And by the way, I want to just do it today, so I won't have to do it tomorrow. This is a simple circuit which has all standard elements, a battery. Actually, and related to this question because they're all connected in series to each other. Then a switch, an open switch has infinitely large resistance. Electrons cannot jump across it. So now I'm connecting to this, well, it's basically a toy. Electrons. And now I'm completing the circuit, connecting this toy to a bulb. And now I'm connecting the bulb to the battery. And what's going to happen? What do you think going to happen? What do you think going to happen? Nothing, because the switch is open. I have to close the switch. And the closed switch represents an ideal wire, zero resistance. You can see the bulb, and now we can see. What do you see? Do you see electrons? We cannot see electrons. They're too small. What do we see? It's just a representation of some charges traveling through the circuit. But can you tell me, those dots, do they represent positive charges or negative charges? Well, you should ask me which terminal of the battery, which electrode of the battery is positive. The red is positive usually, the black is negative. Positive, so that means those charges travel through this circuit from high to low. That means those are not electrons. Those are fictional positive charges, positrons, or whatever you call them. Actual electrons in this circuit travel opposite to that. All right, what's going to happen when I open the switch? No current, everything stops. And of course, the number of electrons traveling through each element here should be the same, because they cannot escape the root, they cannot escape the wires. So the same number of electrons traveling from the battery through the first resistor and through the second resistor, same means same. Electric current is the same. The same amount of charge travels every second. But voltage, of course, split, divided. And this is not new, because when we had capacitors connected in series, again, voltage splits between the devices. So, and again, the same relationship between individual voltage and total voltage remains true. So we can use this now to ask a question. What single resistor can we use to replace those two? So this is our goal. We don't want to use two resistors. We want to use only one with the same battery, but that one should have the resistance equivalent. And what does it mean? It means the current in my simpler, imaginary circuit should be the same as in my original, actual circuit. Electric current should be the same. Well, the Ohm's law says this for a single element. The Ohm's law says this for this single element. The Ohm's law says V2 equals I R2. And we also know that for any elements devices connected in series, total voltage is equal to the sum. So I times R equivalent should be equal to I times R1 plus I times R2. Can we make it simpler? Can we? How? So the result is 4 resistors connected in series. The equivalent resistance is equal to the sum of individual resistances. Why? Well, because basically what we're doing is we're making wire longer and longer, so more and more resistance. That's it. So you see, sad, happy. Well, of course, that's not the question to you, but we gotta answer this question. And we know when we have elements connected in parallel, now they share the same voltage. So, this is just a definition of this element. When we have circuits, a point where we have several wires, not 2, 3, 4, we call it a junction. What is happening at the junction? Those imaginary positrons, they reach the junction and then they split. Some of those go this way, some of those go this way. So electric current now will be different. However, the law of conservation of charge tells total amount of charge should remain the same. So if I add current number 1, current number 2, maybe 3 or 4, I should get the amount of the original current. That's the first thing to remember. And that's what we call the junction rule. Next time, just have it sit right here. I know you have to leave. Now, I know he has to leave. For each individual resistor, of course, we can write the same law, the Ohm's law. This voltage will be equal to this current times this resistance. This voltage, we say this, but we know it's the same as this. They all have the same. Will be equal to this current times that resistor, etc., etc. And now, if you do some algebra, you can prove that for resistors connected in parallel, to calculate the equivalent resistance, we have to use inversed resistances, which is kind of similar to 1 over C, right? So mathematically, not different from 1 over C equals 1 over C1 plus 1 over C2. What is the difference between capacitors and resistors? For capacitors, this equation was used for connected in series, capacitors connected in series. But for resistors, we use it when they connected in parallel. Why? Because every time when we are adding a resistor in parallel to another resistor, we give more room to electrons to travel through. That decreases resistance. Now, let's see that it actually works. All right. Let's see if we can see. So we used a decayed capacitors before. Now we're using decayed resistor. The decayed resistor is just a box with a set of resistors. We can change the value. This one is set to 10 kilo ohms, and I have another one, 10 kilo ohms. And this device, well, this device can measure everything: voltage, electric current, and electric resistance. And I want to use it to measure electric resistance. So how do I do it? Well, I just have to connect the wires to the resistor. 10 kilo ohms. 10 kilo ohms. Now, what do we expect to see if I connect these two in parallel? In parallel means I connect electrode with high potential to the electrode with high potential and low to low. And you can see that it gives electrons kind of more room to travel through. So the resistance should go down. And it does. But if I connect these two, one after another, it essentially increases the length of those wires. So what do we have to see now? Instead of 10 and 10, it will be 20. And we will use this device later again to measure electric current. You're going to be using a smaller version of it, something like this. Well, there are helpful analogies which I would recommend to keep in mind. So electric current is like, oops. Well, technically I can just read it and transmit it to you telepathically. Can I? You never know. So there are certain analogies between electric current and just a flow of any fluid. And when a resistor is connected in series, it's like two different pipes with maybe different diameter, and the battery acting like a pump, making electrons move through. And electric current is similar to like a charge flow rate. That's what it basically is. Yeah, not volume flow rate, not mass flow rate, charge flow rate. That's what electric current is. This is the summary, and technically now you can solve any problem related to any circuit. We haven't talked about power yet, but it's just one more equation. So, well, you're ready for the exam, and I can cancel class for the 3 days. But I won't. Question. What do you think about this situation? I'm going to prepare this circuit. I have a switch, I have a battery, and I have a bulb. I don't need this toy. So I have a battery, I have a switch. Oh, also have a capacitor. All right, I'm going to put it back. This is my capacitor. So this is like an extra bulb, just a neat toy. Oops. So what do? I'm imagining that I am that fictional positive charge which will have travel through. So I'm starting here. That's where I begin my walk. I will have to walk through this. Then when the switch will be closed, I will walk through this. Then I will have to walk through this wire reaching the capacitor. And after the capacitor, I have to walk here. My circuit has to be closed because I cannot jump. And then to the wire and back to the battery. The switch is closed, open, and when the switch is closed, what might happen? Well, is basically based on our understanding what a capacitor is and what a capacitor does. A capacitor is like a big jar, an empty tank, or an empty bucket, but that bucket will be filled eventually. Oops. I want to make it exactly like it was before, so plus was on. All right, let's move it backwards, like it was before. All I did, I just inserted an extra element. Inserted an extra, well, it might take a while. So, first of all, if we made a change to a circuit, any kind of a change, for example, just closed the switch, we have to rewrite the circuit. We have to rewrite it, redraw it, redraw. This is what is happening now. And here, those fictional positive charges start traveling through the bulb. They reach the capacitor. And what is happening next? Question, can electrons or those fictional charges jump across the plates? No, they cannot, which means eventually when capacitor is completely filled, everything should stop. So of course some charges, because of the pump, because of the battery, those, some of the charges have been moved away from another plate of that capacitor. But again, it can happen forever. So when capacitor is almost filled up, electric current getting slower and slower, less and less electrons can travel because they're being repelled by those which are already there. And so electric current is not high anymore to make the bulb bright, but we can still see there is a little, but if we wait longer and longer, see, they travel slower and slower. Eventually, when the capacitor will be completely filled at its capacitance, that's it. There will be no electric current anymore. But what's going to happen? It's not a question, but what's going to happen if I remove the battery, I close the circuit again, but not with the battery. The switch is still open, so the circuit is broken yet, but what's going to happen if I close the switch? All the energy capacitor stored in it now is being released back in the circuit. And it's actually large amount, large enough to make the bulb on, but you see over time, what's happening again? It's not the battery. Only battery can provide the sustainable voltage for a long period of time. The capacitor just gives away wherever it's stored. And it takes, of course, certain time, but not infinitely long time, not days, minutes. Couple of more minutes, and that's it. It's going to be completely dark. However, the current will not be zero for some longer time, because it's a 1 farad capacitor, and 1 farad is, well, million times more than 1 microfarad. All right, so we're not going to be solving specific problems related to a combination of capacitors and resistors. That's first and last, just to demonstrate the reasoning about physics for a circuit like that. But you, of course, can expect, and you have at home, problems related to capacitors only and resistors only. Now, we've said many times that the battery is acting like a pump, but the battery is not a capacitor. You see? in order to make the battery work for a long period of time, something else should be happening inside. And that something else has a name, EMF. Well, hundreds of years ago, people called it electromotive force because they thought something mechanical was happening inside. But now we know it's not the case. We know it's a chemical reaction, a certain chemical reaction happening inside and separates charges between two electrodes. But the name stays, we just shorten it to EMF, just two letters. So when we say the voltage of the battery or EMF, same thing, that's it, that's the same thing. And of course, we treat all batteries as ideal, so no internal resistance. That's not the case in general. Every battery also has some resistance. We neglect it, set it to 0. We neglect the resistance of the wires. The only resistance presented in a circuit is in a passive device, in a resistor, in a bulb, in a motor, anything. Now, the thing is that if we have a positive electrode and a negative electrode, there has to be electric field between those two electrodes. An electric field should point from a high potential to a low potential. But electrons inside the battery should travel opposite to that. And that's what EMF does. It's like a person who picks up an electron and physically moves it against the force acting on it. That's what it does. The source of EMF in the battery is chemical, but there is also electromagnetic source we're going to talk about later, Faraday's law. And there's another analogy which some people find helpful. A battery is like a ski lift. It picks up a charge, brings it up high, and then the charge can slide down on its own. And then the battery again does the same work again and again. All right, thank you very much. Yeah, I know.